It's my pleasure to welcome you all to this talk. This may be the first of many. Midori, as I'm sure all of you know, is a project that's been going on for about 4 or 5 years now under Eric Rudder. And what it started with was a research prototype that Galen and I built, Singularity, and it's done a lot of fascinating work to actually turn it into a robust operating system that's in use now inside Microsoft. The goal of this talk is to introduce Midori to a larger audience, both the researchers and I see people from the rest of the company as well, in the hope of getting more interest and more both research and development on Midori. So this is just a kickoff overview talk. The Midori team is actually quite interested in talking to other people about using Midori. They're quite open about making the sources and so forth available. So turn it over to Joe, and just remember, this is just the tip of the iceberg.
Great. Thanks a lot. Thank you for inviting us to talk, Jim. So my name is Joe Duffy. I'm an architect on the Midori team. And basically going to give kind of an overview of the system. It's going to be quite a bit of content to cover in the time that we have. But that said, I'd love, if there are questions along the way, please pause me at any point if you want to go deeper. If there's things that aren't clear that you wanted additional detail on, just feel free to interrupt. So what is Midori? Well, Midori, as Jim kind of mentioned, is a systems incubation project, kind of looking at the entire software stack from the bottom all the way up. And really, if I could distill it down into a single, you probably saw this in the talk's title, a single theme, it's really safe concurrent applications that interoperate with Windows. So why is that interesting? Well, there are a lot of disruptive hardware trends happening, obviously, over the last 5 years plus around multi-core heterogeneous processors, the shift to not just supporting Intel, but also supporting ARM and mobile, and tackling tough problems. So we see a lot of challenges in security, correctness, the scalability, the responsiveness of Windows programs. We'd like to solve those as well. At the same time, though, we are taking a no legacy look at the entire software stack, which is great. But we have, as a company, a lot invested in Windows. We've built up this great ecosystem, this great. We've learned a lot over the years. We've had a lot of success. So of course, we want to leverage all that success and carry the company forward, while still kind of innovating in a no legacy environment, which is kind of an interesting challenge. And so we did start, as Jim mentioned several years ago, started with the Singularity ideas, which were pretty interesting in terms of software isolation. And we really looked at, hey, how do we make this into a shippable system where we can run production workloads? And as we'll see later, we're actually running some online services for Microsoft in production as we speak. And just a quick mention of kind of how we work as a team, because it's somewhat unique as well. We started in the early days, there's more research, incubation, and over the years, it's become more and more like shipping a product. All along, though, we have had a strong engineering culture. And so we do, thorough design and code reviews. We do automated tests for, everything, including several browser components, for example, at 100%. We do take code hygiene and performance very seriously. And perhaps most interesting of all, the team is all developers. So, even if somebody's a manager or a lead, they're writing code actively. Even if somebody's got the title of architect, they're writing lots of code. In fact, our first rule for the team is everybody codes and everybody loves to code. And we don't make exceptions there, which actually leads to a very interesting culture. I've worked at a bunch of product teams and incubation teams at Microsoft, and I feel like this to me is the biggest improvement culturally that the team has made. It's really, everybody feels passionately about their code and their component, and they really take responsibility for the thing from start to finish, including writing test cases and performance tuning. We do a very open architecture and coding process, so weekly design reviews, and everything's out in the open code review aliases. Debate is the norm on the team, which I think leads to a much better product. So I think the takeaway here is we're doing some interesting research, but we're also engineering a product at the same time. And we have this past year, as I mentioned, shifted to online services. And it's been an interesting experience trying to apply that same rigorous culture that we apply to building the operating system itself to online services. So, incorporating stress and test coverage into all of our release criteria. And I would be remiss if I didn't note that we are hiring. We're always hiring for great people. So in terms of the technology, the architecture of the operating system, this is it in kind of a single slide, trying to highlight some of the unique aspects of the architecture. So we do run, if you look at the bottom of this diagram here, and I'll try to use this pointer, we do run on either virtualization, so Hyper-V, or the bare metal. And we do support multiple architectures, so x86, x64, and ARM. This recent year we moved to the Tegra 3 SoC. And so the base of the system is running in what we like to say the policy-free microkernel. That's one of the only aspects of the system actually written in native code in C++. There are a few others that I'll mention later. But most of the interesting things that you'd expect out of a kernel, memory management, resource management, I/O, is the domain kernel here. And so as we go increasingly further up in the stack, everything becomes managed code, something we call Midori C#, which is basically C# as you know and love it, extended with some Midori-specific systems programming features that I'll cover later on. One additional aspect of the system which is interesting is that we don't do demand paging. So we have this philosophy that we like to call no lies, which means we don't do transparent virtualization of resources. We leave it to the program to manage its resources. The kernel itself gets in on the game in terms of resource management. And instead of allowing processes to basically overcommit the system, instead we prefer to shed load to stay within the realm of responsiveness. And this is actually one of the keys that lets us really outperform Windows in terms of responsiveness and maintaining programs with bounded and expected behavior. Maybe the most interesting aspect of all is that the whole system is, as I mentioned before, running in Midori C#, which means it's type safe, memory safe, concurrency safe, and we use capability-based security throughout the system. So it's not ACL and identity-based. It really is capability-based, which you can do if you have a type-safe object-oriented system. This includes third-party code and device drivers. I have a bit more to talk about with device drivers later on, but a device driver really to the system is not special. It's not running in kernel mode. It's not running in protected mode. It is just an ordinary program. We do isolation, kind of belt and suspenders in depth. So similar to Singularity, if you look within what we call a domain is a single address space. And yet you can see there are multiple processes within this example domain. And so we use type safety for the isolation between these processes, which is lightweight, and we can actually share some memory by reference if it's immutable, for example. But this is purely possible because of the fact that the whole system is type safe. Then this is an example of if we had code that we didn't trust, we would need hardware isolation in depth. We can actually use what we call a domain to do that. So this is an example of running Excel in Midori using a technology from MSR you might be familiar with called Drawbridge, which provides a really nice story for hosting untrusted Windows applications on the overall system. So again, stop me if anybody has additional questions here. So as we look at how the system appears to the programmer, this is kind of our little mission statement. We really are targeting, and I'll just highlight the purple parts, developers of ordinary skills. So this really is targeting the high-end .NET developer, for example, C++ programmers. A lot of the system is geared towards systems programmers that are writing code for Windows today. And we're really aiming that what the developer writes is safe, scalable, just by virtue of the way that they've written the program. So this kind of leads to one of our mantras, safety and correctness by construction, which really means the development platform strives to give developers constructs that are correct, secure, responsive, high performance by default, so that a developer doesn't have to write code and then have to go and profile and find out afterwards that they use something incorrectly. One of the areas that this really comes up is allocation. If you look at a lot of managed code abstractions. They really are allocation heavy, and naive use of those leads to horrible performance, especially on the server. And so we've spent a lot of time really making sure that the primitives we expose to people are high performance and will be competitive with native C++ code. We do have a language which is a derivative of C#, where we've basically taken parts that we would never support, like reflection and dynamic, and left those off the table, interop, and those sorts of things, and added things around improving our ability to static analysis. So we like to say if it compiles, it's safe. This includes device drivers. So for example, we have no mutable statics in the system. We have a first-class notion of immutability, isolation. We do have a modern error model that I'll talk about a little bit later. I'm sorry?
Do you have shared memory?
Yes and no. The question is, do we have shared memory? So we do have sharing, but when running between parallel workers, the sharing is only immutable data. So there's no races against shared immutable state. But we do take advantage of shared state for immutable things, and where we can share things by reference without making copies, for example. So I like to say C# productivity with C++ performance. So by virtue of the fact it's managed memory, GC based, we eliminate a whole class of errors, and we actually see this in practice as we've brought up workloads on the system. And we've had to come up with clever allocation-free ways of doing common things like taking a subarray, dealing with strings and that sort of thing. Safe concurrency is another kind of very important principle, which means essentially no race conditions, deadlocks. We don't expose things like threads and priorities to the developer in the classic sense. And a lot of concurrency comes for free based on the fact that you decompose your program into many small, lightweight processes. And finally, best-in-class developer usability and productivity, which means essentially, we use the company's tooling wherever possible around Visual Studio. And so the Midori development kit, the MDK, which you'll see referred to later on, is fully integrated with Visual Studio. So you get a nice kind of F5 experience, and you can use the project system. So it feels familiar. Essentially, any developer outside the company walking up to this that has done a reasonable amount of .NET programming should be familiar with how things work. That was one of the tenets. So I hinted at the device driver model earlier, but I thought it was interesting to talk about this in the context of everything I just mentioned, because device drivers follow that same model. So third-party code isn't running in ring 0 in the processor. It's not running in the kernel itself. It's all verifiably type safe. It runs in its own process, so failure of a device driver is not catastrophic to the entire system. It's a separate question as to whether the chain of dependent processes can survive that failure. In many cases, the answer is yes, but obviously that's a kind of a design point. All device drivers on the system are based on a rich framework for third parties who want to write device drivers. So it's not a special device driver SDK. It really is just part of the overall programming model. And the framework's largely declarative. So if you look at just in terms of lines of code, our SATA driver is 60% smaller than the Windows equivalent, and yet just as feature-rich. Our NIC drivers are a similar story, including our 10 gig NIC driver. And if you look at why this is, a lot of the code in device drivers is actually there to handle the inherent asynchrony of the device itself. So there's a lot of queuing and queue management and locking, and it's very error-prone for all the same reasons writing that same code at higher levels is. And so since we've spent so much time in the Midori programming model dealing with concurrency and queuing, we really just reuse all of that investment to build the device drivers, and we see a large reduction in lines of code as a result. And it's just easier to get correct.
If your driver runs as a process, failure is isolated, and then why is it necessary for all the third-party code for those drivers to be verifiably safe?
Why? Well, the question is why, if everything is verifiably safe in terms of user code, why do the drivers need to be verifiably safe as well?
No, my question is, you already isolate the drivers in a separate process. Why do you
Right.
also require the third-party code to be done in a verifiably safe way?
I see. So the safety of the isolation between Midori processes, if I were to go back here, if you look at these processes here, the safety of those is dependent on the type safety of everything in the domain. Because if a process over here could violate type safety, then this process over here is at risk as well. And so imagine this was a device driver and this was a user process. Well, a failure of type safety in either one of those would put the entire domain at risk. So when that's the case, like for example, Excel, which was compiled for Windows, we stick it in a different domain and have the hardware isolation. And the device support, it's a blessing and a curse because we have to write all the device drivers, which means inherently we can only support a finite number of devices, not architecturally, just because there's only enough hours in the day to write device drivers. But that said, we do run on lots of standard SKUs. The Dell 50X100 desktops, we're running in Bing on the standard autopilot SKUs. We support virtually all of them. In fact, we recently were delighted to find that most of the new Windows 8 laptops, for example, the X1 Carbon Touch laptop, we have no problem booting and running on those. And so over the years, we're kind of accumulating more of a basis for running on modern hardware. So we do have a complete client and server-side networking stack. So TCP, HTTP, UDP. We support HTTPS, TLS on the client and the server. One of the interesting bets that we made in the networking stack was zero copy across the system by using immutable buffers. So this is actually a significant advantage compared to a lot of Windows workloads that we run, where getting a network buffer that's DMA'd into from the NIC all the way from the lowest level in the device driver all the way up to the application, maybe the web service, and allowing it to parse some data out of it. Often in Windows and with .NET, you end up with several copies being made, which obviously impacts your locality, and you just spend cycles doing copies. And this actually carries over for IPC between processes as well. So we'll see later on, you can have a pipeline of processes, the NIC DMAing into a buffer on one end, transferring between processes all the way down to the web app, and not a single copy has been made. And this actually tends to be a pretty significant advantage. And again, we've achieved this performance without sacrificing the security and safety, so this is all sticking to our principles. And we do, often do transmit file benchmarks and just raw throughput benchmarks, and we can drive a 10 gig NIC at wire speed using this. And in this last year, because of the focus on bringing this up in the data center, we paid a lot of attention to security. So we did a lot of fuzzing with Codenomicon and a few other tools that you can license for doing kind of typical net stack fuzzing. And it was a great validation of the safety approach because there wasn't a single remote execution exploit that we discovered using tens of thousands of out-of-the-box replays of common networking attacks. And this is just an example to put some things in perspective of where we came from. So if you look on the lower left-hand side, this is the classic benchmark spec web 99. Which is basically a web workload where you're just fetching files as fast as possible, and the client will rate how many requests finished within a particular latency ceiling. If you look all the way on the left-hand side, we started with a lot of headroom, and mostly, I picked this to come after the network slide just because you can see some of the improvements like software TSO and then hardware TSO, DMA channel, 10 gig NICs. You can see as we've kind of really fleshed out the networking stack, we've become much more competitive in terms of the networking performance. So back to the development platform a little bit. So the MDK itself is, as I mentioned earlier, all Visual Studio based. We reuse as much as possible and replace only what's necessary, which turns out to be mostly around the language service since we've done some innovation there. The build system, we do have some new tools around async debugging. It tends to be kind of a pain point no matter which system you're on. And in terms of the innovation in language, we've really stuck to the error model, which means we've done exceptions and first-class contracts, requires, ensures, kind of Eiffel-like spec sharp-like. Done a lot around lifetime analysis and stack allocation. We've found that to get great performance, with the whole system being GC-based, really minimizing time spent in GC has been critical. I'll touch on that a little bit later. And the system, in terms of how it's packaged and delivered to developers, is very similar to .NET and Windows 8, in that it's based on reference assemblies and MSIL, which you can kind of look at with Reflector and any other standard MSIL-based tools. This is, you look at, this is a kind of a very high-level view of the framework that we offer. So the main takeaway here is it's a fairly complete framework, from supporting, asynchronous streaming and text encoding, standard collection types, all the way up through the driver framework, multimedia. We do support audio, video, AV sync, storage stack, networking, JSON, XML, link over those things. And then, higher up, we do support some higher level programming models around, web server-based programming, client-side web programming, graphics, and test frameworks. So it is a reasonably complete system. That said, it's not 100% complete. We still have a fair bit of work to go, and we're focused on fleshing this out mostly in conjunction with the workloads that we've been chasing. Yeah.
How much of this class library stuff we're able to fork and port from the existing .NET class library?
So the question was, how much could we port from .NET? And the answer is as much as possible. So let's take a good example is XML Reader. So we knew we wanted a streaming XML reading API. And so we started with the .NET design because we wanted something that's familiar to programmers. And if we can reuse what the company's already built, we wanted to. So we took that, and for the most part, we could use it. But it turned out the places where we had to change were around allocation profile. So the allocation profile is something like 2.5x the size of the document you're parsing. And we really, one of our principles, we wanted to do it in a zero alloc way, to be able to parse the thing, use the stack as much as possible, reuse buffers as much as possible. So that's where we chose to innovate. It did impact the API a little bit, but for the most part, it's in spirit. It looks a lot like .NET. And that you can see that same recurring theme kind of all throughout.
So do you think some of these innovations would go back to C#, especially with respect to OLI and things like that?
So the question was, do we expect some of the innovations to feed back into C#? And the answer is, I hope so. We definitely talk with folks on the CLR team, the C# team, and in fact, we do language reviews with the C# design team, and they're definitely interested. And the one we did most recently was the work we did around stack allocation, because we did find that to be really crucial to a lot of the workloads we've tackled. And in fact, some of the async work that happened in .NET 5 or C# 5, we actually collaborated and shared code with them as well. So we do look for those opportunities wherever we can. Some of these are more radical changes that are harder to retrofit into the language, especially no mutable statics by default. That's a hard one to retrofit, although we constantly look for ways of doing it.
So when you mentioned JavaScript there as one of the languages, does that mean that most of the APIs are also accessible to JavaScript programs, or?
The question is around JavaScript, what surface area of the API is available? And the answer is it's mostly just standard JavaScript. So we haven't done much work around exposing the services, although it's definitely interesting to us. We've talked about potentially using TypeScript to expose typed APIs for these sorts of things. We'll see later the message passing for asynchrony. That might be we actually think that might be a more promising way of allowing JavaScript applications to reuse some of the OS services. But for now, it's mostly just for UI and standard browser cases.
Across processes?
So the question is file system across processes, and basically, yes. So there's the file system itself. There's a SATA driver, and those are processes, but the file system itself is a process. So you can say, hey, open a particular file, and then you can share that capability with other processes, basically. Yep.
Earlier you said you can achieve C# productivity with C++ performance. You're giving some example like allocation free. Can you comment on can people use .NET? Is just a programming practice, or is it some new support, a new requirement you put in there so that the developer can achieve those things?
So the question is, can you just achieve the C++ performance without having to code to a different programming model? And the answer is they kind of go hand in hand. You know, if you didn't have the frameworks that were built with allocation freedom in mind, you'd end up losing a bunch of allocations there and losing performance by using existing APIs and existing services. So unfortunately, I think they go hand in hand. You can probably make some progress by doing ahead of time compilation of C#, which is essentially what we're doing. But I do think the whole thing kind of goes together. So in terms of the concurrency model that we have, I kind of broke it down into these three kinds. One is process level parallelism. The second is task parallelism. And the third is data parallelism. And I just wanted to give some examples of the safety. So, you know, we do make it easy to create processes that are truly isolated, again, using type safety. The RPC mechanism, which we'll drill into in a little bit, feels a lot like C#. You know, you have the await keyword. There's some subtle differences between our await and C#'s await. And the task parallelism one is maybe more interesting because it shows, hey, you know, I can have immutable data structures. I can spawn tasks and use those immutable data structures by reference without having to marshal them. But perhaps what's most interesting, and you can see that down here, is with the data parallelism case, if I try to perform any sort of side effects, that's a compile time error. And so, you know, the same would apply to the task parallelism case. If I captured a list and tried to add to it, for example, it would say, sorry, you can't do that. And so we do kind of, this is one extreme where we're saying, you know, we're going to hold the line and we're not going to allow race conditions into the system, but it actually allows us to do optimizations based on this. It allows us to give basically perfectly strong memory models to the developer without actually having to compile with fences everywhere, for example, because we control all the points of fork and join. It allows us to have value type delegates, for example, which you wouldn't be able to do without this guarantee because value type delegates necessarily are multi-word. And if you allowed race conditions, you know, racy access to those, you could tear it and completely break type safety. So it enables kind of a whole host of new optimizations that wouldn't have been possible otherwise. And none of this would work if we didn't really embrace immutability and isolation in the language. So we do have deep immutability throughout the frameworks. For example, you know, comparers in the system are immutable, and we enforce that at compile time. It's part of the language.
Task parallelism, is there a reason to choose one over the other?
The question was why would you choose process parallelism over task parallelism? The way I think about it is process parallelism is more of a, you know, it requires some design. You have to create an interface for your process. But it allows you to have state over time, right? So you can have the notion of a history within the process itself. You have a rich interface into the thing, so you can have multiple different kinds of functions. Whereas task parallelism is more of an anonymous process, if you will. It's basically, hey, I've just got this delegate. I want to run it in parallel. Please do it and give me an answer. It's more of a one-shot kind of thing. Often what I find is people will start with a task, and then over time they may kind of evolve in the direction of a process when they realize they need more functionality and a richer way of interacting with it. So despite the several versions of, you know, ways that you can access parallelism and concurrency in the platform, it is all built on top of one holistic scheduling and resource management architecture. And so, you know, we do have kernel and user mode schedulers that are working in conjunction with one another. Most of the system, interestingly, is scheduled cooperatively. So in a well-run system, we virtually never see preemption because we have cooperative scheduling at multiple layers of the system. This is great because it leads to more effective use of quanta and warmer caches as a result. Another interesting thing, just like we use device drivers, you know, device drivers are just processes. Interrupt dispatch is really exercising similar pathway for delivering messages into user processes, which means that thing's got to be pretty efficient to satisfy interrupt dispatch, which means you just, you know, get the value as a programmer just using the system as you would. All user code is what we call non-blocking. Oh, yep.
So in cooperative scheduling, I can see why being able to define the points at which you preempt or rather don't preempt, at which you switch, is beneficial for cache behavior. But does not, the fact that you are encoding in the application when the reasonable boundaries are, how does that, when the underlying architecture changes, does that mean that the application has to change to expose longer quanta, for example? Mm-hmm. So do you end up embedding more knowledge about the characteristics of the underlying architecture in the code?
So the answer is, statistically speaking, no. So what happens is the cooperative checks are not in the program code. They're in the schedulers themselves. So at every possible opportunity to check with the, up in the runtime scheduler, every possible opportunity to check with the kernel to say, hey, do you have more important work to do? If yes, I'll give you back the worker. It does so. But the program is responsible for basically having what we call turns that are bounded in length. And a turn is basically from one await to the next, right?
The idea is that the program exposes very small granularity time units, and you tend to run many of those before you
That's right.
schedule it away.
That's right.
Okay.
And in the worst case, we do have preemption, but we like to avoid that if it.
That's the
Yeah,
case
no.
of the program.
Right.
Yes, to make one of those opportunities available.
Exactly.
Okay.
The link stacks, are they more for the dynamic stack growth, or do the coroutines span more than one method call?
Yeah, so the link stacks, it's basically, so anytime you start an async activity or a task, let's say, a new link stack is procured, and it starts off very small. As the program executes, it will link and accumulate more stack as it goes, but it's for the duration of that particular async activity. It does span method calls, and we do a lot of work to hoist and eliminate, stack probes and stack checking. For synchronous code, it all runs on a flat stack, so there's no actual probes. So it's really the point at which you say, hey, spawn a new async piece of work. That's when we jump over to the link stack and kind of go from there.
So what's a link stack? I don't know.
So, Windows programs generally have a large contiguous stack of 1 megabyte, or it's based on policy. It's typically 1 meg. Once you hit the end, you hit the guard page, which is basically game over. You've overrun the stack, and that usually leads to stack overflow, which in .NET programs kills the process. So for our case, we wanted to use stacks, and we wanted to use blocking code because it's great for efficiency. But at the same time, you don't want a 1 meg stack for every small async activity. That would kill scalability. So what we do instead is when you start a new async activity, we procure as small a stack as possible. I think our theoretical minimum is 256 bytes. Then from there, as you're hopping, you can grow based on some policy that you...
Oh, you have so discontinuous allocation. And then you
Discontinuous,
fix it when you
that's
return
right.
from methods or something like
Exactly.
that.
So as you return, there's a thunk that does the unlink and returns it to the free pool, for example.
Back to this question about the cooperative scheduling. If I'm writing CPU-intensive code, then do I need to insert kind of time or some kind of command to say I'm like giving up? I can give up control now.
So the question is, if I'm writing CPU-intensive code, do I have to insert checks to give up control? And the answer is generally yes. We have tools to help out, but it's, if you don't do that, you could potentially starve a queue somewhere. So it's definitely one of the disadvantages to
Someone else's.
generally your own queue. Because of the fact you can preempt, it's only within your process, so you kind of impact your own responsiveness to the message queue at that point.
So when do you preempt?
So it's based on policy, but it's basically, the cooperative flag gets set. It's kind of a double preemption, right? The cooperative flag gets set, and then after some period of time after that, say 10 milliseconds, if the app hasn't responded, then we preempt and we can dispatch a new worker and service whatever workload is necessary. And then that thing just is a parked stack just like any other, like in Windows scheduling, right? So it's really based on policy.
So if you don't yield in a CPU intensive block, the only person you're hurting is your own app.
That's right.
Okay, fine.
Yeah. So as an example, last year we built a Midori link client. We wanted to prove out, the resource management architecture, the scheduling architecture. And if you, compare the result, and we have a video, should include the link for this. Basically, under load, on Windows, you end up with many, many threads, different priorities, trying to juggle kind of the resource consumption and requirements of the machine. And yet, even with that, it kind of breaks down under stress. And it's kind of remarkable to see, the Midori program basically, uses 17 processes because everything's decomposed into processes. Just uses the scheduler, the cooperative scheduling, and it actually vastly outperforms the Windows version to the point where, the program becomes almost unresponsive and you get the standard kind of spinning donut kind of thing, and yet on the Midori side it remains perfectly responsive, which we thought was a nice testament to kind of the whole scheduler architecture and resource management. So the application model, which is basically how do you write a program for Midori? Well, a Midori program is very different from a Windows program in the sense that it's naturally decomposed into many processes. Whereas, on Windows, you'd create a program, it would be one process. Maybe you go out of your way to create multiple threads. Maybe you'd use the thread pool. But in general, you wouldn't think to decompose it into these asynchronous agents that are communicating with one another. And that's kind of the standard way of breaking this down for Midori. So the browser, for example, our browser, is 8 processes by default when you launch the thing. And it's great because, well, first of all, you get this natural asynchrony in the program. But it also gives you the ability to take advantage of multi-core, right? Just kind of without having to really work hard at it or contort yourself or do unnatural things. It just kind of comes standard as you write your code. It's the standard kind of RPC mechanism I'll show you in a second where you've got a server part and a client part. We like to say, when I say capability-based security, capabilities in the system really are these. They're basically proxies to services in other processes. And they're all kind of asynchronous. So all communication over these proxies are asynchronous. They're transferable across processes. So if you send a message to another process, you can mention the capability, and by virtue of mentioning it, the other process now has access to whatever that capability represents. It is used for all system services, including I/O, network, and it's not forgeable. Again, we're using type safety here for the security model. So this is nice because everything is asynchronous, concurrent, responsive, and high throughput. So if I look at kind of what does this look like to the programmer, well, there are really 4 steps. One is you basically declare your interfaces. So every process in your program has an interface, and it's written in C#. So I might have a speech engine service interface here with a recognized method. And there are certain types that you can mention in these things. So immutable data by reference. Other capabilities, a stream is essentially a kind of capability. Then during build time, for the most part, this happens behind the scenes. You don't have to know much about it, but it's basically doing generation of abstract server-side stub that you then have to implement in a client-side proxy that you can use to interact with this thing. It's a standard RPC kind of service-oriented system. So then on the server side, I say, hey, here's my implementation of the recognize method, and you actually stick code in there that compiles. You override this base method. And then from there, you're ready to go ahead and use the service via its client-side proxy. Now, creating these things and discovering services kind of depends on whether you're using a system service, whether you're just creating a sub-process within your own process. But again, it really looks just like C#. And here's a concrete example. So what I might do is if you look at the code first here, if I have an audio stream, I might say to some manager, hey, give me an engine process, and maybe that thing's doing caching or pooling. And in fact, in our implementation of the speech server, that's exactly what it's doing. So I say, hey, give me an ENUS speech engine. From there, call the recognize method on it. And notice this looks just like a method call, even though there's RPC going on underneath it. And notice in the Midori programming model, if you don't see an await, there is no blocking. So when I call recognize, there's no blocking that happens. I'm immediately given a speech result. So all of this is pipelined. I'm kind of offering up speculative work as I go along without actually doing kind of back and forth synchronous RPC. And then from that, I might get recognition text, which gives me this async result of T thing, which if you're familiar with .NET is kind of similar to a task of T, except it's much lighter weight. It's a struct. If it's promptly resolved, then it's just basically a struct wrapper around a T. So there's another example where we really paid attention to performance. And then if I actually want to extract the string out of that thing, then I can await And that's the thing that blocks my coroutine link stack. So the nice thing about some of this is if I look at classical synchronous RPC on the left here versus async RPC, well, the typical thing would be, send the message, wait for the response, send the next message, wait for the response, send the next message, wait for the response, and then finally write the thing out. And obviously that's inefficient for a number of reasons. One, you're waiting for all the round trips and wasting opportunity to offer up more work to the system. Two, you kind of handicap the system. It can't do as much in terms of batching of communication. So if you look at what we actually do, we'll execute the 3 calls promptly, queuing messages into a buffer, and based on policy in the IPC channels, we'll decide when to actually deliver those things. We can do efficient batching. We can do flow control if we need to impose some back pressure. And then finally, write out the text. But what this basically means is in a heavily loaded system, you've kind of got lots of work built up in buffers and kind of improves throughput overall. So I've kind of hinted at the error model a few times now. We felt like, the C# programming model or error model wasn't exactly kind of what we wanted. There were some interesting experiments, in Spec Sharp. There was a lot of great work done there that informed what we did. But the first principle was, fail fast discipline. If there's a bug, then we should stop running code immediately. Throwing an exception, allowing code to back it out or catch it and swallow it is definitely not the right thing to do. So that led us to really make a bet on contracts. And so we actually have language support for pre and post conditions. We do a lot of compiler analysis to take advantage of this in the backend compilers. In fact, this turned out to be critical when we look at taking some workloads like speech recognition, where it's, you would assume that the overhead of managed code around bounds checking, overflow checking, you would assume that this would kind of handicap you. But by doing a lot of these more sophisticated analyses with range propagation and taking advantage of pre and post conditions, it actually improved the quality of our code. And this really is the 95% case where most .NET programs would use exceptions. We're using contracts instead. So for example, argument null exception, argument out of bounds exception, those sorts of things just become contracts.
So contracts are purely compile time, or they also have a runtime component?
The question is, contracts are runtime or compile time only? The mental model is that they are always present at runtime, and if the compiler can prove that it does not need to run at runtime, then we'll elide them. But we do actually use these for kind of cross-module compilation, virtual calls. In some cases, you can't actually prove that the condition holds or does not hold. We do actually use exceptions for some things. So for dynamic and recoverable failures, for the most part, this tends to be things like parsers, I/O, some of the IPC mechanisms where a process may fail and you may have to deal with it. And by default, methods can't throw, which is great because as you're scanning code, I find it clarifying, to know that only all the points of failure are explicitly called out in the code. And the compiler can actually take advantage of that and perform optimizations based on the fact that, hey, code can't throw, it can elide exception handling metadata, it can be more aggressive about code motion. In addition to just a single bit saying whether a method can throw or not, we do have a form of checked exceptions. So you can actually say, hey, I throw and I only throw this set of exceptions. And once you've done that, it's similar to all the there's subtyping implications of that. There's versioning implications of that down the road. But it turns out to be useful just from a documentation standpoint. We do also disallow taking dependence on dynamically thrown exceptions. So if I call an API and it says, oh, I fail, and you just happen to know it throws a foo exception, you're not actually allowed to catch that exception directly because that's basically taking a dynamic dependency on unstated behavior. So if the author of that API wanted to enable that, they would have to say, hey, I throw an exception, and oh, by the way, it's a foo exception. And finally, we do have deterministic destruction for eager resource reclamation. My favorite example is a secure buffer where you want to ensure that for this block of code, you're going to use some secure data and you want to zero it out before you've actually exited that block. We don't have classic finalizers in the system, so we do have deterministic destruction.
When code's using like arrays or memory allocation or division, does it have to declare that it can throw out of bounds exceptions or out of memory exceptions or divide by zero exceptions?
Right, so the question was around numeric code. So by default, numeric code fails. So it's fail fast if it overflows or divide by zero. But we do have APIs for using those if you want like a Boolean that you can check yourself.
And is running out of memory also a failure for the whole process?
Yes, running out of memory is a failure for the process.
Non-recoverable.
Yes. Yep. In general, any failure, even we call it abandonment, the fail fast, even that sort of failure is recoverable if you have another process that's kind of watching and deciding how to recover in the face of that. So it's not really true to say it's not recoverable, but within the process it isn't. You can't catch it and keep proceeding. So there is a storage stack. So we support FAT. Oh, go ahead.
Sorry. If running out of memory is by default is fail fast, and you don't page, how do you manage that tension between using available memory and backing off? Because optimal resource usage for RAM is to use 99.99% of it for your optimal caching or whatever, and then back off when it becomes full.
Right.
How do you orchestrate that?
So it's a combination of things. One is having applications aware of the resource usage and cooperating with the operating system, which knows everything about all resource usage. So caches, it can dump memory from caches if necessary. So if you're using the system caches, for example, they'll unload for you and kind of shed load as necessary as the OS detects that you're under load. There's also persistent state, right? So you basically have to always be prepared for the fact that, hey, you may be killed under extreme circumstances. And so any important state needs to be journaled, right? So that it can be recovered upon restart. But in general, it's really kind of a delicate balance with the app cooperating with the OS and subscribing to certain notifications and saying, hey, the load is increased to a certain level, unload as much as I can. So like the speech server is a good example where it wants to run as hot as possible, use as much memory as possible to keep all of its engines in cache, but under extreme load, or if it's loaded too many engines, it's experienced a peak load, for example, then it gets notified from the OS, hey, you may want to dump a bit of your memory consumption, and then it's a trivial thing to do because it hooks into all of the caches provided by the OS itself, right?
So if I'm using the right high-level objects in my program, in your framework, then internally those objects are hooking into this channel to the OS that tells them how much memory, what the memory pressure is like. And
that's right.
As a programmer, I don't have to worry about that.
Right. That's right. If you're using the built-in services. Now, a developer may go off and kind of write some ad hoc cache on their own, which obviously our best practices document would say, hey, don't do that. But if you do that, there are notifications bubbling up from the OS that would allow you to build such an efficient cache yourself. But if you get it wrong, then the consequence is the OS may decide, hey, we asked you to trim load, you didn't trim load, so sorry, goodbye. Okay? I mean, the theory is that the program itself is in the best position to decide what resources are important, how to virtualize them. Once the OS does it, I mean, you get into the situation that you often have, in Windows where things are paging out of control and there's kind of no intelligence to it and everybody's trying to use as much memory as possible. So we said, hey, we're just not going to get into that business. We'll kind of give it to the app, leave it to the app. And in practice, you end up with bounded resource usage, bounded time. Accessing memory doesn't potentially lead to disk accesses, for example.
I agree with all that. I guess the worry is just that when you have perhaps less disciplined programmers writing apps for this system, you get into a big spate of it works for me bugs, where
Sure.
somebody builds something, works for them on their machine, and it doesn't work for somebody else who's happens to be running several copies of the program or something like that.
Which is definitely a risk. And I think it all comes back to trying to encourage programmers to use best practices and use the abstractions that we kind of offer in the platform.
As a Windows guy, I'll give you a counter argument. If you're in the same situation with paging, it's the same experience. It's just your screen is frozen paging rather than your app abandoning cleanly.
Yep.
You'll lose your Word document. Right? Windows will churn along and eventually page enough stuff in to save your document. This thing will fail fast and kill Word. Unless we're as careful in German.
So the storage stack, we do support fat storage for interop and SMB, but we do have a native file system as well that's kind of designed for what we call modern storage devices and applications. So targeting really SSD instead of spindle. It is kind of like a transaction, more like a typical file system where it's log structured, append only. Space reclamation happens with kind of a garbage collection like policy behind the scenes. And the way a programmer tends to interact with this is through defining data schema in C# and then using basically a similar technique to what we saw earlier with message passing to essentially serialize the data and create kind of convenience helpers for dealing with the underlying data store. And interestingly, if we look at the file system in the classic sense is actually just an abstraction built on top of the record-based log structure underneath, where I basically say, hey, here's a file record. It's got a path. It's got a name, creation date. And these really are, this is the way we build the file system, is actually mapping these high-level records down into the actual structured storage underneath. So I mentioned before, we spent a bit of time last year getting into the data center, so actually running some online services. From day one, we kind of architected the system for what we consider next generation cloud support, knowing that the next generation data center, code and data deployment is more policy based and cloud based. And so we actually worked with the Autopilot team to get up and running in Bing's data center. Running with Autopilot is basically the manageability fabric underneath it all, which includes doing kind of automated deployment, servicing, reinstallation. You can think of it as Midori server kind of looks like a Windows server to the overall infrastructure. But we have invested a lot in making sure that these things are, services are debuggable with events, perf counters, crash dumps. So it really is kind of a first-class integration into the data center. And along with that, we spent a lot of time kind of developing the overall web programming model, again, for some of these online services. So we have a full, web server with HTTP, HTTPS support. It is highly configurable. We have, classic way, kind of like servlet style interaction in the overall object model. But we've also got ASP.NET Razor up and running in the last year, which is essentially a lightweight ASP.NET programming model where you've got ASPX pages with some markup mixed in with code. And built on top of the overall web server, we do have a web services stack with XML, JSON support. We're looking at supporting Bond as well, which is kind of what Bing tends to use these days for service serialization. And the nice thing that I think we've done is unify that programming model for the web services with the overall programming model for message passing. So if you look at, I don't know if you remember from earlier slide, we declared an interface for inter-process communication using this eventual attribute. Well, you kind of start the same way with web service, then kind of augment it with the web service attribute as well. And that basically does all the code generation for you behind the scenes for generating client, same model, client proxy, server stub that you go and implement. And then through decoration of the different parameters here, you can say whether, well, first, it's a RESTful API, so my path is query. I can say, hey, give me the content type in this parameter here, query string parameter locale, and so on. So it's kind of nicely integrated. You don't have to program the system two different ways.
So can you comment on that? This web program, so relate to the drawbridge. If you run whole bunch drawbridge in, say, the servers, and compare with running whole bunch drawbridge on Windows server, can you compare them? What's the benefit by doing that on Midori?
It's interesting. I wish I had numbers. We actually were just talking last week about doing the experiment of running ASP.NET in Drawbridge on Midori, run it full out, do the benchmarking versus running natively on Midori. I have some slides coming up in terms of the overhead of running programs in Drawbridge. My feeling is you probably lose 10 to 20% of your overall throughput, but it's definitely an experiment that we want to try. So this is just a bit of a case study. A considerable amount of work last year went into making this happen. But we basically, we had our annual meeting with Steve, and Chi was there, and we said, hey, let's go. Everything looks great. Synthetic benchmarks look great. The demos look great. Let's pick a real production workload and see whether we can get it up and running. So we picked speech recognition. We'd already been working with these guys for a while because they have interesting and unique requirements. We also think it's important to the company going forward. If you just project out Windows Phone growth, more immersive experiences, simple arithmetic tells you, hey, it's probably going to grow in usage between 5 and 10% over the next couple of years. And yet, if you look at kind of the speech literature, it's challenging to both hit the latency requirements and the quality requirements at the same time. Basically, if speech could get 2x the CPU, they would happily take it and consume it and deliver better models. But in fact, right now, the service is basically struggling to just keep up with real time, just because it's very computationally intensive. So we said, that sounds interesting, sounds important, let's take it. So we started with the C++ code and really architected what we thought a modern speech service would look like. Basically 370,000 lines of unsafe C++ code, kind of standard C++. And at the end of the day, kind of whittled it down to 115,000 lines of Midori C#. Again, no cheating, so there's no unsafe code in there. It's all safe concurrency, all safe code. And the results were actually quite good. So we've been taking about 20% of live Windows Phone traffic as of December 12th. And in fact, if you talk into your phone in this area, the way we've done the load balancing, you're almost guaranteed to actually hit the Midori servers. And the results were basically 40% latency improvement, while at the same time 3 to 4x better density and capacity, so better throughput in the data center. And we've since taken those gains and actually spent them to do deep neural networks in conjunction with MSR and the Bing team, which has actually improved speech recognition quality quite a bit. This is kind of an extreme example, but one of the reasons why all the code, the code size was dramatically reduced is if you look at the code, there are a lot of points of unsafety, a lot of blocking code. It turns out the code actually had a lot of locking in it, so it was multi-threaded. So there were critical sections, interlocked operations. Obviously, lots of manual memory management, which we got to delete most of that. Manual streaming implementation, and the whole thing was H-result based, which led to I don't know, maybe a fifth of the code was just handling H results and shuffling them back and forth. So it's an extreme example, but that was actually kind of our experience with quite a bit of the code. And the concurrency was the same thing. They actually had to manually implement their own thread pool and tasks and scheduling algorithms and played around with priorities. And it was quite a bit simpler at the end of the day after we converted it over. So this is kind of just a summary of the performance. Basically, the main takeaway is that more than triple the load, the latency gains are visible. So if you look, just going from the Windows Phone numbers, if you look at, there's one concurrent request, 9, 18, 27, and 28. So currently the cap on the system is 9 for the Windows production system is capped at 9, because beyond that, as you can see, server latency goes from 762 to over 4 seconds, and so that's kind of where the knee is. So they won't schedule beyond 9. And then beyond that, presumably because of queuing and resource contention, it basically hits the wall and doesn't finish the benchmark. So we were able to actually both improve, if you look at the left hand of the curve, about half a second better latency, and still stay under the the latency ceiling, which we set to be what the current server had at 9 concurrent requests.
So did you do any comparison either with this project or another project with regular .NET, regular Windows? Just to have an idea of where the part of the benefit that comes from the OS and the part of the benefit
Right.
that comes from a managed framework.
So I would have loved to do that, but my feeling is that it would still be a similar experience, because one of the real key things our experience doing this workload was GC time. It was really important to keep that at a minimum, especially for a server program that's under heavy load. Oftentimes you talk to people around the company, they have workloads that are 30, 40, 50% GC time. We've actually really, that was a KPI from day one, performance that we watched. And we did keep it under 1%. And so I feel like the only way to do that is if the entire server architecture, the set of APIs, the abstractions that you're using are allocation free themselves. The other thing that I kind of alluded to, but I haven't talked about in too much detail, is backend compilers. We actually have a set of optimizing backend compilers as well that turned out to be quite an asset when we did the work.
Another quick question. Did you have to redesign the GC or just adapt to new APIs?
We didn't redesign the GC. In fact, I hinted earlier at reusing some native components around the company. So we are actually using the Red Hawk CLR GC, Workstation GC. The JavaScript engine, for example, we took IE10's JavaScript engine. So we didn't tune the GC. We really did tune the data structures to be more GC friendly, have fewer allocations, and those are the major changes we made to the speech algorithm and data structures itself.
Can you comment on how many man-years have to be spent to do the rewriting?
How many man-years did it take? Well, we did it in conjunction with the Bing team, so we were kind of in it together. It took, roughly 6 months to get to the point where we had interesting results, and I don't know, it was half a dozen to a dozen people kind of at varying points during the project. So it wasn't, we were smart about how we did it, so we actually, stopped at managed C++ along the way, and then wrote a full Lexer parser for managed C++ that spit out Midori C# on the other end, so that definitely sped up things.
So did you need the vectorization capability to get for the sketchpad?
Absolutely. So we definitely needed SSE support.
So you do have a vectorizing
Yes. We do, but we actually ended up using a lot of manual vectorization for the Gaussian mixture model code, where it was really, that was kind of critical to hypertune that thing. But the good news is it's all type safe, so we paid for the bounds checks where we had to pay for the bounds checks. But we definitely needed SSE. And the same thing with the deep neural networks as well. We needed to use SSE there to be competitive. And this is just a quick, this is something interesting that we've done. We open up the gains, and so half a second of savings on speech recognition may not be impressive. It's definitely noticeable to the end user, but the more interesting thing is what you can actually do with that half a second. You can actually, in this case, we're using technology deep neural networks, which, neural networks have been around for a long time, but only until recently with the kind of hybrid deep belief networks, the HMM plus DNN model, was it feasible to run this in production from a performance standpoint. So we're actually now running this. We have a prototype. We're going to flight this in April, but it's actually promising. So it's actually faster than, if you look here, this is the original latency, 1.45 seconds on average for this corpus, and we've dropped it to 0.85 with DNN, which is obviously a significant reduction, and at the same time it delivers an improved word error rate. So the standard way of measuring in speech recognition is how many words did you get wrong in the recognition, and so this is the relative reduction in word error rate thanks to DNN. So I don't want to get into too many details, but the main thing here is that we can give better performance and a better user experience kind of at the same time, which is pretty exciting. And just one more case study, just quickly, so just so people don't think, hey, speech was the only benchmark we did good on. I already showed SpecWeb 99 earlier. This is maybe more interesting, SpecWeb 05, because it's a more modern benchmark. It's basically 3 web workloads banking, e-commerce, and support. And this is comparing, against the Windows on the same hardware using HTTPS and hyperthreading. And the overall, it varies based on the benchmark, but the overall improvement is 59%. It's measured basically, again, like SpecWeb 99, how many conforming connections are there, which means how many requests finished within a certain latency threshold. So we often get the question, why is performance great? So SpecWeb 05, for example, is just part of the benchmark. You're not allowed to touch it. We can obviously change the web server and the architecture underneath it, but in terms of the application, it's hands-off. Speech recognition, we did change a few data structures algorithms mentioned earlier, mostly around locality and improving the interaction with the garbage collector. But if you look at kind of the overall sum, I think, is you get much better locality, and the whole process model where each process has its own GC heap of mutable state that's kind of compactly represented in all immutable data structures like the grammars and networks are shared by reference amongst all of them without any copies. Couple that with a zero copy I/O pathway, and we actually even saw this in the CPI numbers. Much better, more efficient cycles per instruction. The safe concurrency, the fact that we didn't have to take locks, we didn't have to play tricks with interlocked operations all over the place, definitely paid off. Scheduler, I think I mentioned earlier there was a custom thread pool, and kind of being able to just use Midori scheduler and believe in it was kind of a big thing as well. And then I alluded to this just a few minutes ago, the whole backend compiler where we could actually do stack allocation optimizations. We can do aggressive interprocedural, intermodule optimizations, really do all that we can ahead of time at compilation time. Actually paid off quite a bit. And we had a whole compiler team that was kind of looking at the benchmarks as we went and finding opportunities to do better, get rid of struct copies, kind of things that you see in most managed code. And the nice thing here to highlight is 25% more is on its way, mostly around profile-guided optimizations. We brought up a new PGO framework, which for speech itself delivers between 12 and 20% alone.
So I was a little suspicious when you said no locks. I thought you meant you were lock-free, but no, you really mean no locks. So let me say back to what I think you said. You tell me whether I've got it. When I write code in a conventional concurrent manner, maybe I'll have a big monitor protected data structure that has multiple methods, and those multiple methods have to be able to run concurrently to be able to get scalable performance over this big data structure.
Right.
I think what you're saying is the reason that your system avoids that fate is it's a programming discipline. You don't write those things anymore. You find all the immutable pieces and you take them out of there so that they don't have to be protected by a lock.
That's
and
right.
the few pieces that are mutable are now only ever executed on a single CPU, so you don't have to lock over them? Is that
That's right.
Okay.
Right.
So
they're isolated within processes where you've got kind of all the mutable state is generally packed together, and then any immutable state is, as you said, shared by reference.
You don't run into the case where you have a big convoluted pile of state that is both mutable and you need concurrency accessing.
That's right.
And that happens because of a change in how programmers think about structuring the data structures.
Right.
Okay.
Right. And that's why I tried to emphasize earlier that the programming model really is about decomposing your program into a bunch of processes, and mostly the decomposition is around state, right? What are the different logically distinct isolated pieces of state in your program? So for example, speech server, every engine is an isolated process. Every engine has its own local mutable state, but then I might have 10 engines loaded for ENUS, and they're all sharing the same underlying grammar and model and state, but it's all provably immutable. So we do, I focused a lot on the server side, and this last year for us was mostly around server and cloud, but we do actually support modern UIs. So most of our investment here is around HTML5, really betting on Windows 8 style UI, having the same story for web apps and rich UI apps, which means declarative specification, doing all layout via CSS. And for the most part, we try to reuse assets again, just like across the stack. I think I already mentioned the JavaScript engine, but also Direct2D. Anything we can reuse, we do. But one of the key things is really taking all the architectural principles I mentioned already and applying them to UI. So trying to essentially make it, quote, impossible to suffer the screen bleaching problem, where you have STAs that are failing to pump. And our UI is all based on functional reactive programming.
What's an STA that fails to pump?
Oh, sorry, single-threaded apartment. It's kind of, the way message pumps work historically in user 32 in Windows is all around pumping for messages, and then if you have blocking code while you're pumping, then do you pump again and suffer reentrancy, or do you risk hanging the UI thread? It's kind of a delicate balance that nobody ever gets right. And obviously, the fact that this is all safe code and capability-based security means that things like UI injection attacks, escalation of privilege, are just difficult, if not impossible, to pull off. You'd have to violate type safety somehow, essentially, to do these things. So we do use FRP, functional reactive programming, for the inner workings of the UI model, which is actually quite nice because as you're doing a UI evaluation, you don't have the classic problem of whether an update took place. If you're dealing with a partially updated UI, a partially updated kind of state model behind it, it is all consistent. It provides basically consistent snapshot in time where as I'm performing this evaluation, the world isn't changing out from underneath me. We have spent a lot of time making FRP perform well. The classic model is to declare your UI as boatloads of objects with boatloads of dependencies, and then you need to track all these dependencies and know when to do the reevaluation. We've actually spent a lot of time optimizing by upsizing the behaviors. So usually an entire tree is a single behavior with a single dependency on another tree. And by doing this, we can have a more efficient representation. We can save on memory, fewer GC pointers to chase during collections. And overall, this was kind of the trick to making FRP perform to the level we thought it needed to compete with kind of classical UI models. There is a browser, which, well, first, every OS needs a browser, but also, there's a good opportunity to validate the UI model for the overall system. And it's not complete. Actually, implementing HTML5, CSS completely with full compatibility is quite difficult, but we did pick a reasonable subset where most of the web actually looks reasonable. So we can run, for example, HTML5 Canvas with Cut the Rope. We can run Facebook and W3C. Most websites look reasonable. We do have a lot of work to go. We've made some good progress. I think next year we'll probably increase our focus on a client-side workload. As I mentioned, this past year has been mostly around server. One other thing to note is we did take the IE10 JavaScript engine and fully integrate it into the runtime. So it uses the Midori object layout and all the link stacks that I mentioned earlier. So it is fully integrated with the system.
When you say you integrate the JavaScript engine, do you require it to be written in C# or it's a native code, you package it in your system?
So today it's native code. It's kind of an implementation detail. I would say in the ideal shipping system, it would be written in Midori C#. From a tactical standpoint, that would make it much more difficult to actually share code and take FIs from the Chakra team who's continually making good progress. So I think the day will come eventually where we say, hey, we need to rewrite this in C#, but we haven't done that yet.
It means it's not safe. You're just assuming it's safe, right?
That's right. Yes. So definitely we're depending on that code generation being correct for type safety. We have talked about, hey, should we put it in a different domain? And I would say if we were going to ship a client program today, we would have to make a decision there. And it probably would be to put it in a different domain. So we're kind of just keeping that decision at bay for now. I mentioned earlier, we are kind of making a bet on the modern UI. So we actually took the weather application from Build. I don't know how many people remember this, but it was nice because it's mostly JavaScript, HTML5. We had to change very little of that to get it up and running. In fact, we created our own Midori version of Win.js, which allows us to run a lot of these programs. But I think the main takeaway here is just the bet on the web is actually allowing us to get up and running on the client faster than we would have otherwise.
So did you do any performance or responsiveness analysis for the UI applications?
So we do have some numbers. I didn't show them today, but around standard JavaScript benchmarks, like SunSpider, and those, and we definitely are competitive. Some of them were better, some of them were not quite so good. I have to admit we haven't mastered the art of measuring responsiveness. In fact, we had a review last week where some architects on IE were suggesting, hey, we should get together and brainstorm about the best way to measure this. So we're definitely gonna do that. So I mentioned drawbridge at the beginning. I'm not going to spend too much time on it, but it is really a nice app compat story because it means you can run PowerPoint. It looks like just a hosted window within Midori, and the performance is within the realm of reasonable. There's just a small overhead. This is running natively on Windows versus the same thing running in drawbridge on Midori. You can see startup time is very reasonable in terms of 200 more milliseconds for Excel, and it's kind of in line with the anecdotal number I gave you earlier of 10 to 20%.
Sorry, when you say Windows native, is running drawbridge on Windows native or running the native application?
Running the native application on Windows, no drawbridge. One of the numbers we're looking to compare is drawbridge on Windows versus drawbridge on Midori.
Yeah.
We don't have those numbers here.
You don't know if the overhead is coming from drawbridge or coming from drawbridge.
Right. And I think, as you pointed out earlier, getting similar kind of comparable server-side numbers would be interesting too. So final section here, just wanted to mention the backend compiler. So we do have Bartok and, oh, go ahead.
Question, are you doing demand paging for drawbridge or overcommit and things?
Demand
Seems like Excel's a tight fit in memory.
No, we're not doing demand paging for drawbridge. It is a tight fit depending on which spreadsheet you load. It is an interesting question of what the user experience would be under overcommit in that circumstance. I don't know what that would be though. Okay, so we do have a backend toolchain, Bartok and Phoenix. Bartok came from MSR, and Phoenix was a project in DevDiv. We've kind of taken them, integrated them together. So we do have a ahead of time compilation story for both C# and C++. Actually, it's MSIL based, so it's not just C#. And the nice thing about unifying these backends is, all the standard optimization improvements to native code to make C++ code competitive accrue to the managed code stack as well. There are quite a few managed specific optimizations we do, especially around, struct copying, some of the things I mentioned around stack allocation and GC layout. The other thing to note is we do take advantage of Midori execution model where possible. I think I have a few examples coming up soon. And again, we do target x86, x64, ARM Tegra 3, and MDIL. And this is just an example of just to show, hey, we're competitive on some standard benchmarks. So this is a C# integer benchmark, benchstone on x64. You can kind of ignore this number because it includes fib, which was compiled down to a constant, which isn't very interesting. So everything else is. So this is both are higher is better. So this is against CLR JIT compiler. This is the engine compiler. So basically 24% in all cases. This is speed, not space.
Sorry, which one's yours?
Oh, sorry, this one.
Oh.
So you can see this is the ratio. So green is good, higher is better. So the overall ratio is 24% faster.
In cases where you're worse, why?
We have done the analysis. I don't know off the top of my head, unfortunately. But yeah, I would hope that at the end of the day, we wouldn't be worse in any of them. But overall, it's a good mixture.
It looks like this is something you really should give back to DevDiv, right?
Yeah, well, we share conclusions. We talk with those guys all the time. So, yeah. So this is Spec 2K6, x64, O2. This is the Bartok Phoenix, well, mostly Phoenix backend compared to the shipping VS compiler. So in this case, this is speed, so higher is better. This is space, lower is better. So the basic takeaways, here, roughly competitive. In some cases better, some cases not. And so we looked at, why some of these results. Well, profile-guided optimization is, those numbers didn't include it, but that for speech particularly is kind of game-changing. A lot of the overheads from managed code we thought would actually show up in speech. We were actually successfully able to optimize away, often through bounds check hoisting or better range analysis. We did do SSE, as I mentioned earlier, and we did a fair number of interprocedural optimizations for managed code. We're not whole program. We are actually, the system is based on basic DLLs, essentially, or modules. But we do have, interprocedural inlining and those sorts of optimizations. I didn't mention earlier, but because of the frozen or the immutable statics model, no mutable statics in the programming model, we're actually able to evaluate all statics at compile time and freeze them into the read-only segment of the binary and share them across all processes, which is actually kind of neat. Even if you say, hey, new list of objects equals, in your static variable, we'll actually freeze that whole thing. So we do full-blown MSIL interpretation at compile time. And we do whatever little class initialization is required after that at process startup, mostly for GC statics and that sort of thing. But what it means is it's actually surprising if you look at the code quality for a lot of managed code, it's kind of sprinkled with class constructor checks, and that's an overhead we didn't have to pay. So really, the theme behind all of these was look at the managed code, look at the native code, why are they different, and try to eliminate any overheads that are intrinsic to managed code. And again, developer experience I mentioned is a big thing for us. So compiler, throughput, debug builds. People coming from a managed environment kind of expect, hey, I'm just going to run the C# compiler and then JIT the whole thing. Turns out the C# compiler is very quick to run because it's not doing optimization. So getting our overall ahead of time compile time speed down was actually, is still to this day, a continuous focus for us. So wrapping up with 3 minutes to go. So I think it's been a big year for us. We felt good last year about the architecture performance. Now we're actually running something in production with kind of good results. So I think it's a good data point validation of the unique architecture shown earlier. And what's next for us is basically continuing momentum into production and kind of stabilizing some parts of the platform. Continuing to look for partners, workloads in Bing, Azure to keep getting experience with the platform. Eventually, I think next year we'll start looking more at the client and getting kind of a real workload running there. I did want to point out all of the design notes are open, available to FTEs. Feel free to browse there and give us your feedback, ask questions. One of the points of doing this talk was try to open up collaboration with other folks around NSR and across the company. I think, as Jim mentioned at the beginning, we'll probably do some more follow-up talks to drill deeper into things like the file system, the scheduler, concurrency model, the programming language. But definitely, if you have any feedback, we would love to have it. And even listen to the code and play around if you'd like. We are hiring. And that's it. Any questions?
So earlier you showed this speech recognition runtime performance gain.
Yes.
So as you know, there are basically two processes. One is the computing the score, local score as a frame. Now when you change from GMM to DN, you probably will change.
Yep.
And the other one is the search, to get it from the out. So on both phases, do you have relative numbers as to what kind of gains you get from Gaussian mixture model to DN? I
don't know them off the top of my head, but we should talk afterwards. Most of the difference was in the front end with the scoring, but we did see secondary effects because it was much more aggressive at pruning hypotheses. So we did see that we spent a lot less time in the engine searching the search states because presumably there were way fewer. But we should talk about that.
I guess a little bit surprised. It seemed like the part of the motivation for Midori was getting safety and reliability. Mm-hmm. It seems like the main selling point you've been using is better performance.
Right.
Is that just because that's the best way to sell things in the company, or is it safety and reliability not that useful? Or?
Yeah, it's a continuous struggle. I think it is ironic, but it tends to be something that resonates more with people, and we can actually deliver tangible, measurable value. It's really hard to put a number on reliability and safety, whereas it's easy to put a number on, hey, the customer waited half a second less for his answer. So that's been mostly, so the hope was, great performance and, you get all the safety improvements as well.
What's the Midori approach to GPU programming?
GPU programming?
Yeah.
So right now, we're working on a GPU driver. We don't have something yet. We're actually running with Warp. So it's all Visa with Warp currently. We do have a programming model where we kind of sketched it out for vectorization and said, hey, we can do this for GPU as well. But it's very early days on all of that.
So it's in the works then?
It is in the works. It's primarily gated on really getting a native GPU driver up and running though.
So I don't really quite expect you to answer this, but there's a bunch of really smart guys looking over a bunch of stuff. How much of the gains you're seeing is a result of sort of the C# infrastructure versus just being clever?
So it's a question we get a lot, and that's why in the slide, I really do believe the slide I put up there where it is mostly the architecture, the fact that you've really separated mutable versus immutable state and been very deliberate about that, which I think you could do some of that in.
That would help for everybody, right? I mean, that's a matter of.
It would. But the thing for me is the extent to which the programming model guides you in the right direction and almost forces you to do the right thing versus you kind of have to create your own frameworks to do that. You have to create your own discipline. There's no static checking. The tools aren't there to help you. I do feel like that is the key, is really the concurrency model. The fact that the whole system up and down kind of works in unison with one another rather than at odds. You often find multiple layers of scheduling kind of working against each other, whereas we've been really intentional about distilling it down into an architecture that works together. I think there's some.
I'll take that as a you don't know, but you like what you're doing.
It's hard to quantify. I did read every check-in though, so I do believe that that was primarily the result.
Has Midori adopted the .NET exception handling mechanism, or have they wired their own?
So for exception handling, we have a very different programming model, and we have a very different implementation as well. We tend to use events rather than groveling the stack to accumulate textual stack traces. So we find that the performance is significantly better. So it's kind of, we changed the execution model. We also changed the programming model quite a bit.
I have a question. I'm not sure if you'll be able to answer, but what's the expectation or really the ambition going forward? Is that Midori will eventually be, at some point in time, our customer-facing OS, or is it just a plan B? If Windows fails, we have something.
I would say it's an incubation project. We're hoping to learn some interesting lessons and share them with the rest of the company. I think focusing on the data center has been great because we can more quickly iterate and get feedback, real-world usage, and without having to answer the question of, hey, what do we tell our customers? So I think at this point we're still learning, and we're trying to share those learnings with other teams in the company. I wouldn't make any bolder claim than that.
Sure. A quick question on this sharing knowledge. I heard you mention a couple of times that div, IP, Bing. Mm-hmm. Are you talking to Windows as well?
Yeah. We have architectural reviews every year. We try to meet with the Windows kernel team. So yeah, we talk with those guys.
So I see Azure on the slide, but I didn't hear it mentioned much in the talk. Is there any chance of an OS family equals Midori 1 anytime soon?
Well, Azure is interesting for the same reason Bing is interesting, but obviously there's a customer avenue there, so that's unique about it. I think some of the challenges Azure faces are similar to the challenges Bing faces, and I think recognizing that and helping wherever we can is definitely top of mind for us. We don't have a workload in mind. I put it up there because I look at them in a similar family to one another.
I was thinking more in the case like we use Azure to run our services.
Yeah, exactly.
So could we start writing them against Midori and run it in Azure? That would be amazing.
I think Azure is also interesting because they're experimenting with the drawbridge technology as well. So there's the synergy there as well.
So one question, it seems you did a lot of work on parallelizing things properly, right? But it looks like this is all focused on parallelizing within a single machine. Mm-hmm. So I wonder, are you looking at how to maybe extend that to an entire server farm? And so what I'm thinking is once you are in managed code or a code role, you basically know about every single bit what it means, right? So it means you can do really cool stuff. You can actually migrate entire data structures from one machine to another. You can migrate them also in the other direction into a GPU. You could even recompile for a GPU. So these two things. I wonder scaling out and scaling into the GPU? Are you thinking of like a more generalized or standardized mechanism?
Yeah, so we definitely focus on single machine first because we thought, if we can't do single machine, then we definitely can't do multi-machine. I would say one of the workloads I kind of glossed over is distributed deep neural network learning, machine learning. I know Jim has some folks looking into this as well. I think we're hoping that we can use these sorts of workloads to teach the system to be distributed. We did architect for kind of transparent location in terms of the IPC model and the file system. So there are, I think, we had that in mind architecturally from day one, but we haven't really spent time making it work and building the pieces and the mechanisms that we need. So I'm hoping in the next few years we'll definitely shift focus there. For now, it's all web services, open protocols, and I think that was the right thing to do for now.
So last week, Eric Rudder had this demo in the Tech Fest.
Yep.
They showed the number. Is number consistent with the number you showed here?
Yep.
It was flashing out very quickly. So
Yeah, it was the same thing. Yeah, that Adam was from my team. He gave the demo. Yeah.
So the user experience is really good. Just finding it. Somehow when looking at the number, it kind of helps you.
Yeah, it's much more impressive to see it in person. Yeah. Okay. Thanks again, Jim.